This is Advanced Algebra with Mr. O'Shea. Today we're really going to be focusing on systems of equations, the introduction to it. Specifically with systems of equations, we're going to talk a little bit about what they are, and then after that, a couple different ways how to solve them. System of equations. So we've got two equations here, and we've got 4x plus y is 8, and 2x minus 3y is 18. A system of equations is going to be when you have two equations. So we've got an equation up here in yellow and an equation in green. We've got two equations with two variables. You could have more equations with more variables, but for our focus right now, we're just going to focus on two variable systems. So we've got two different equations with two variables represented in there. Now, what we're really doing here is we're looking for an x and a y that's going to make both of these equations true at the same time. We got some ways to kind of go about solving those. So we'll focus on the first one, the 4x plus y is 8. Now there's tons of different answers that actually make this true. Lots of coordinate points because that's really a line. So any point that's on the line makes it true. So we could take the point 2, 0. If we plug in the point 2, 0 for our x and our y, we get 4 times 2 is 8. 8 equals 8. That point suffices the actual equation, right? It makes it true. We've got other points that we could plug in -1 and 12 into our equation. 4 times -1 is -4 plus 12. Does it equal 8? Yep, 8 equals 8. That's another point that suffices that actual equation. We've got a third one here, 3 -4. Plug that in, see if that actually makes the equation true. 4 times 3 is going to give us 12. 12 plus -4, really 12 minus 4, it does equal 8, so that one also works. And we can kind of keep going with this forever, but for our purposes, we'll stop there, right? So now let's look at that other equation. We got 2x minus 3y equals 18. We'll test a few points on this one as well. Take the first point, 9, 0, and we'll plug it in for our x and our y. So 9 is x. Oops, that's supposed to be 0. So 2 times 9 minus 3 times 0. Does that equal 18? The 3 times 0 is going to give us 0, so 18 minus 0, yeah, that one checks out. 18 does equal 18. That works for our equation. Let's test the second one here. 2 times -3 minus 3 times -8. Does that equal 18? 2 and -3, that'll give us -6. -3 and -18 will give us positive 24. Does that equal 18? Yep, that one works as well. We've got 3, -4. 2 times 3 minus 3 times -4. 2 and 3 is 6. -3 and -4 is positive 12. 6 plus 12, yeah, that does equal 18. So that also works for this. All right, now here's where it gets a little tricky. When we're doing a system of equations, we're looking for the actual answer that makes both of the equations true at the same time, right? So we're looking for an x and a y value that makes both true. If we look at the two, we've got one that will work, right? It has to be the same x and the same y for both equations at the same time. So when we go back, there's one that works on both. We got this 3, -4. Makes our first equation true. Also makes our second equation true. So that, in and of itself, is going to be the solution to our system of equations. It's going to be the one set of points that makes both equations true at the same time. All right, there's lots of different ways how to do that, right? We just did a little bit of guess and check, plugged in some points and found the one that matched for both of them. But you guys can also think of these as graphs. So take, for instance, x plus y equals 5 and 2x minus y equals 4. We can graph these and see where they meet, because really that's going to be the point that they both share. So we'll get the first one in mx plus b form. I subtracted an x on both sides, and we get y equals -x plus 5. And we'll do the same thing on the other one. Subtract 2x on both sides, so we get -y equals -2x plus 4. But I don't want a -y, so we'll divide everything by -1. And that turns it into positive 2x minus 4. So we got two lines. We're going to graph them both. Now these two lines are really representing this y equals -x plus 5. That's our first equation. And y equals 2x minus 4, that is our second equation. change the color here so we can see the graph. Start at plus 5. Slope is down 1 over 1. Now when we graph these, we want to put every point that we possibly can on here. I'll go ahead and connect these. All right. And the second one, y equals, let's change the color here. Y equals 2x minus 4, so we'll start down here at negative 4. And the slope is 2, so up 2 over 1, up 2 over 1, up 2 over 1, so on and so forth. And we can go ahead and connect those. Now every single point that's on this black line, like the point 1, 4, the point 2, 3, 3, 2, 4, 1, so on and so forth, that makes that first equation true. Every point that's on the green line makes the second equation true. We're looking for the one point that makes both equations true. That's our intersection point of the two lines. So the point 3, 2 would be the one point that makes both equations true. That's going to end up being our solution to our system of equations. All right, let's try another one here. X plus 3y is 4, and negative 2x minus 6y is 3. Let's solve it for y. So we'll bring the x over. And we'll divide everything by 3. So we get y equals negative 1/3 x plus 4/3. That's our first equation. Same deal on the second one here. Bring the x over, we get negative 6y equals positive 2x plus 3. Divide everything by 6, and we get, divided by negative 6, right? So we get y equals 2 over 6 is going to reduce into negative 1/3. And 3 over 6 is really just 1/2. So we've got two equations, we're going to graph them both. Now immediately what I notice is that the slope of these equations are the same, but the intercepts are different. Now that's going to be really key here in just a minute. So we'll graph the first one. 4/3, that's just over 1 1/3, right? That is 1 1/3, I should say. This one's going to go down 1 over 3. I think looks about right. Down 1 over 3. Looks about good. There's obviously limitations when it comes to graphing. I mean, these points are close, but I don't know how accurate they really are. Let's graph the second one here. First, let's connect that with a line. I'm going to cheat and use a straight line tool here. And we'll go ahead and graph the second. So we'll start down here at negative 1/2. Now, here's the deal. The slope's the same. It goes down 1 over 3, down 1 over 3. Slope's the same on the other one, right? Up 1, backwards 3, so on and so forth. Because the slope's the same, they actually give us parallel lines. We look for where these lines intersect. Well, parallel lines never intersect. It just doesn't happen, right? If the slope is the same but the intercepts are different, they're going to end up leading us to parallel lines. Now that means something for a system of equations. What that means is that there is no solution that makes both of these equations true. And that would actually be our answer for this specific problem. It's no solution. Try another one. 2x minus y is 3, and 6x minus 3y is 9. We'll solve it for x real quick. Solve it for y real quick. Bring the 2x over, then divide everything by negative 1. That's one graph. And we'll do the same thing on the other one. Bring the 6x over, so it becomes negative 6x over there. And we'll divide everything by negative 3. So we get y equals negative 6 over negative 3 is a positive 2. 9 over negative 3 is a negative 3. So we're going to graph these two lines. Well, the slope's the same, but in this instance, the intercept's the same too, which really means that these two equations are the exact same line. So if we graph the first one, starting at negative 3, up 2 over 1, up 2 over 1, so on and so forth, right? And we connect them. Well, when we go ahead and graph this second line, it's obviously just the exact same line. So we graphed right over on top. Well, where do they meet? Where do these things intersect? Same line intersects all over the place. Here and here and here and here. We have infinite number of points that are actually going to make both true at the same time. So that's how we're going to write our answer. We're going to say that there is an infinite number of solutions. And this is actually the specific answer for this problem. This problem would be an infinite number of solutions. It does not mean every number will work, because if we look at all the points that are not on the line, none of those would work, but everything on the line would. Right? Shorten it up, we'll just call it INM for short. INM is perfectly fine on these. Okay, so you get INM when you get the same line. All right, we'll test one more here. 4x plus 3y is 1. Now I'm going to do this a different way. I'm actually going to go ahead and take this and find the intercepts. So we plug in a point, and if this is kind of foreign to you guys, that's okay. We can kind of cover a little bit more in class on Monday. Or you can kind of do a little research and figure out how to graph lines using the intercepts. Basically, it's like called the cover-up method I know some classes use. So I want to know what is the y-intercept. So if x is 0, what does y equal? It's basically I can get rid of x, because if I plugged in 0, it'd be gone. So solve for y, divide by 3, and we figure out that if x is 0, y is 1/3. We could do that same thing to find another point on the graph by saying what is it when y is 0? So we get 4x equals 1, divide by 4, and you get x equals 1/4. Now those are 2 points on the graph. We can plot those 2 points. Shouldn't be too bad, right? 0 and 1/3 is going to be about right there. 1/4 comma 0 is right there. And we want to connect those with a line. Okay, looks about right. And we're going to do the same thing on the other one. We want 2 points, because if you have 2 points, you can just connect it with a straight line. We'll plug in 0 for x and solve for y. Same thing, plug in 0 for y. If you plug in 0, it's really solving 3x equals 2. Divide by 3, you get x equals 2/3. So now we got 2 points, 0, 1, which is up there, and 2/3, let's change that, make it a little darker. There we go, and 2/3 comma 0. It's about right here. If we connect those lines, it's going to be a slightly steeper angle than the other one. And we see that they meet somewhere down in this area, which is a problem. Because I want to know exactly where. I have no idea. I can get close, but I don't know exact. So graphing in and of itself has limitations. That's what I want you guys to see. I don't know what that point is where they intersect. It's a bad method to use on this specific problem. So we want to go through a couple of other methods that we could use to do problems like this. We've got 2 that we're going to focus on. The first one is substitution. And the second method is going to be elimination. Might be other names that people call elimination, but for our purposes, we'll just call it that. Let's take that problem. 4x plus 3y equals -2, and x plus 5y equals -9. We're going to first solve this using substitution. We'll come back and do elimination in a minute. But let's use substitution. Now, substitution, we look for any variable that's isolated, or any variable that has a 1 for the coefficient. And I see that x. I want to solve for that x. I want to get that second equation to be just x equals. So we'll subtract 5y on both sides, and we get x equals -5y minus 9. Right? All right, now the reason it's called substitution is because I'm literally going to go ahead and plug in, I'm going to substitute in, instead of the x in the first equation, I'm going to substitute in what x really is, which is -5y minus 9. So in the first equation, 4x turns into 4 times -5y minus 9, and the rest of it, plus 3y minus 2. Plus 3y equals -2. We're going to do the quick math on here, solve it through. Distribute the -4, we get -20y minus 36, plus 3y equals -2. Combining like terms, bring 36 over. We get negative 37, I'm sorry, negative 17y equals, add 36 on both, equals positive 34. And if we divide by negative 17 on both, we end up getting y equals negative 2. I realize we go kind of quick here on the algebra part of it. Feel free at any point to slow down, stop, pause the video, rewind, so on and so forth. Once we have y equals negative 2, we're saying that that is part of the coordinate point that makes both these equations true. So all we're going to do is go ahead and plug that y equals negative 2 into one of the equations. Doesn't matter which one. We could pick either one. Plug it into one of those equations and solve for x. So we'll just go with the first one. 4x plus 3y equals negative 2. But instead of y, we're going to use negative 2 because that's what we said y was. So now we're left with 4x minus 6 equals negative 2. Add 6 to both. And we get x equals 1. So the solution to this system of equations that we were just working with, using substitution, is going to be 1 comma negative 2. That's our xy coordinate point that makes both equations true at the same time. Again, that method's called substitution, basically because you're solving for one variable and then you're substituting it back in to the other problem. All right, let's go with elimination now. Now the goal of elimination is to actually go ahead and eliminate one of the variables. You can only do elimination when you have it written with x's, then a y equals a number. Now it could be other variables, but we still want it to be our variables lined up. Whatever the x's are first, the y's then, so on and so forth. Now with elimination, if you guys can tell what I'm doing here, is basically I'm combining the first two equations to give us one big equation. So 4x and x gives me 5x, 3y and 5y gives me 8y, negative 2, negative 9 gives me negative 11. Okay. Now with elimination, I want to do this in such a way that one of these terms cancels out. If we see I have a 5x, so that didn't cancel. I have an 8y, that didn't cancel. And I have a negative 11, that also did not cancel. So I'm going to manipulate one of these equations so that it does actually eliminate. And to do so, I'm going to go ahead and look at the second equation. And I realize that if I go ahead and I multiply this entire equation by 4, and I distribute it through, something might eliminate. So we'll go ahead and distribute it. We got negative 4x. All right, let's rewrite the original 4x plus 3y equals negative 2. And distributing that piece out, we get negative 4x minus 20y equals negative is a positive 36. Right? Now we're going to use that elimination method because when I combine it, 4x and negative 4x basically drops the terms out and I don't have any x's left. 3y and negative 20y, combine those, I get negative 17y. And negative 2 and 36, combine those, I get positive 34. We're going to go ahead and solve it from there. Because the x is eliminated, we just have a y value, and we're just focused on that last problem. Divide each side by negative 17, you get y equals negative 2. Which is great. We can go ahead and plug those back into the original equations. Pick one, does not matter. We'll go with the first one again, 4x plus 3y equals negative 2. Plug in negative 2 for y. So we get 4x minus 6 equals negative 2. Hopefully this looks familiar because it's the same answer that we got when we used substitution. Right? Elimination and substitution, and graphing for that matter, will all give us the exact same answers. Alright, you guys have 3 different methods on how to solve 2 variable systems of equations. You guys can graph, you can use elimination, you can use substitution. It's up to you which one that you actually want to use for it. We'll go ahead and talk a little bit more on Monday about which way is the best way given certain equations and whatnot, what to look for and all that good stuff. If you guys have any questions, please don't hesitate to reach out, shoot me an email, and I will get back to you guys as soon as possible. Alright, see you in